All right, so it's 4 o'clock, so let's get started. Um, so welcome everyone to lecture 12 of CS 545, Introduction to Robotics. So today we'll be covering configuration spaces, a very fundamental topic in robotics. So some logistical things. So yeah, lab 2 is coming up. It's due February 25th. So hopefully you have made some non-trivial progress on it. You could continue working on it after, but you also do have a midterm coming up. So the midterm is March 4th. It's in class. So it'll be right here. And I think there's, according to enrollment, there should be enough room for everyone. So it'll be a bit unusual where I expect that you'll get more people here than right now, for example. Um, so yeah, just a couple of policies. So for the midterm, you can bring in 1 page of like a cheat sheet. So just bring in 8.5 by 11-inch paper. That's like your standard printer paper. You can just write whatever you want on it, front and back, and then you use that during the exam. And I recommend doing it now. And I found that it was helpful to study just by like actually making those cheat sheets when I was taking midterm. Uh, and then there's no extra ingredients, so you'll just have like pen or pencil plus that cheat sheet, and then we'll give you the exam, and then you can just you'll just do it. And then just don't bring any extra paper. We have extra sheets at the back of the exam that you could just use for scratch work if you want to. And then, so yeah, it's going to be like no electronics, including no calculators. But if you want to leave something as a fraction, then that's probably the easiest thing to do. So like some of the questions they'll reduce to, compute this probability, then you can always just leave it as a fraction or as the product of a few terms. And yeah, just try to avoid leaving the room when you're taking the exam. Like if you do have to in an emergency, then you just come up and then like you'll just hand over the exam to us, and then But if you do have any kind of medical related concerns or other things that you're worried about, then just talk to me about it, and then we'll just keep it confidential. And I won't talk about it with the TAs if you also prefer that. Yeah, then I guess the other thing I'll say is that I try to be very unambiguous about what I was asking. So it's very unlikely that I'll answer a clarification question. But if you do have to assume something, you can just write it in the answer. Like I'm assuming this question means this, and then I don't think you'll need to do that. Like the question, I think they're unambiguous, but in case you have some confusion, you could just write that as your assumption, and then we'll try to consider it, even though we don't think it's necessary. Uh, yeah, any questions? I have the Google Doc open if you want to write something there. But again, it seems more useful for when there's a bigger class, a bigger in-person audience. Uh, any question? Yeah.
By like a sample. Yeah.
I yeah, I'll try to provide some sample exam. Like I can't guarantee that it's gonna be the same like length because making an exam is very challenging. Like now that I'm on the other side, like this is the first time I'm making a full exam. So it's like a new experience for me. But I think what I'll try to do is next week, Monday, we'll give some example question during class that'll be like similar. And yeah, this weekend, I'll see if I have some time to get a couple of questions. I just can't guarantee that it's going to be the same length as the full one. Yeah. Yeah, and then we are working on grading homework too. So I'm hoping we can get that back to you before you take the midterm. Yeah. All right. And yeah, the stuff we'll cover is basically everything that we've covered in class up until next week Monday as well. Until next week Wednesday as well. So we'll try to cover questions that are like more fundamental instead of like really minor detailed like research paper, like questions that you can only get from reading a research paper, for example. So All right. Well, with that said, though, let's talk about configuration basis today. So let's go through some definitions. So the configuration of a robot is a complete specification of the position of every point of the robot and the minimum number of real value coordinates that we need to express this is the degrees of freedom. So one quick question is, well, you might look at this definition and say, well, you have to specify every point on the robot. Do you think that seems very doable? Like you have to specify every point. Aren't there an infinite number of points? How do people get around this? So what happens in practice is most robots, they're composed of a set of rigid links. So you might have like a base of the robot and then a rigid link that points upward, and then another rigid link that extends out of that. But so even though you can have like an infinite number of points that describe it, you really only need a much smaller number, a set of numbers to actually equivalently express that. And that's what we mean by here, the minimum number of real value coordinates. So we'll see some examples of that later when we talk about like what is the dimension of this robot. And a configuration space is a topological space where every element X and Q correspond to a valid configuration of the robot. So it's like this abstract space. We'll go through some example where like every point in it is one possible way that the robot could be like. Yeah. So every configuration of the robot can be identified with a unique element in Q. So Q is just the wording that we use for configuration. We also call it a C space, or like C space. Like I'll use that later in today as well. And so again, in this class, we will usually talk about rigid objects and robots with known shape when we talk about configuration. So if we work with a robot, we will usually just assume that, we know the model of the robot, like we know how to describe it. So like it might be specified with just 3 numbers or 4 numbers. And so if you want to know about like configuration for things like cloth and other deformable objects, then we will probably save that for later. Because what is the minimum number of real value coordinates that you need to represent a cloth? Think about that. Any idea? So you represent a cloth with 2 numbers. Like take a look at that jacket over there, for example. That jacket in front of you. Can you just that jacket right over there? Can you describe that with 2 points? Like you fix 2 points, but then you have other points of the jacket that move. That's a different element in the configuration space. So let's think about that, and we'll discuss it more near the end of the class. But let's talk about some simple configuration for now. So if you're wondering where I get a lot of these figures, it's from the Modern Robotics textbook. It's listed in the reading, and they have a bunch of really nice lecture videos as well. So this time the book is actually freely available. Like the authors intended it for it to be freely available instead of like someone downloading it and then just releasing it on some random website. So it's a very good book, by the way. So look at this figure. We have to think about like what is the minimum number of real value coordinates that we need to describe these objects. If we have a door and we assume the door is like fixed here, then it can only move in around one axis, then you can describe the entire configuration with just a single angle, theta. So that's 1 number. That's all you need. Again, we're making assumptions like, we know the door is there and it's like rigid and it's structured this way, but, sometimes we abstract away those details. So, here the door, we can describe it with 1 number. again, you might disagree, but then you should also probably like back it up with different assumptions on maybe the structure of the door and so on. And if you have a point and a plane, then you can describe its configuration with two numbers, right? Here's the x coordinate, here's the y coordinate. How many numbers for this coin? I mean, I did one and then I did two, so this is probably three, right? So if you want to describe where a coin is, you can use two numbers for a position, but because the coin also rotates, like unlike a single point math, here it actually matters like where it's oriented, because if it's a different orientation, it's like a different configuration. So this angle is like the direction where this person, Abraham Lincoln, is looking at. Yeah. All right. So remember that we talked about degrees of freedom, like what are the minimum number of of coordinates that we need to describe like something. And if we look at this example here, it's basically describing, if we have a planar object, or later if it's in like 3D space, what is the minimum number of real valued coordinates that we need to specify a configuration? Yeah, so how do we calculate the degrees of freedom of a single rigid body? All right, so let's assume that we are looking at A. So this is like a coin that's flat on a table. So the way that you can derive like the number of degrees of freedom is thinking about like, what do we need to describe it? And then also, what are the constraints involved? So there's 3 points on it. So we have A, B, and C here. What we can do is we can compute distances. So this is indicating the distance from point A to point B, and then from point B to point C, and from point A to point C. So this is your standard Euclidean distance formula that, yeah, I think everyone here has seen. Now, the key assumption that we're making is that we have a rigid body. So we're assuming, the coin is rigid, which is a safe assumption in practice. So in a rigid body, the distance between any 2 points must be constant. So if you move the coin, the corresponding point A, B, and C, they have to move in a way that preserves their distance. So starting from this, in order to calculate the degrees of freedom of this, then here's how we can do this. So we've already identified like the point, but we should start by specifying where should they be, basically. So when we have to choose like where point A is located, because we have no real constraint, there's two numbers that we have to specify, the x coordinate and the y coordinate. So if you assume that this thing here is where point A is located, because we have fixed point A, then what happens to B? So the distance from point A to B, it must be this DAB term that we covered last slide. And what happened there, it creates this dashed circle centered at A, right? So when we pick where point B should be located, what is like the minimum number of coordinates that we need for that, basically? Because the key intuition here is that we cannot just pick B to be arbitrary. Like we have to pick B to be such that the distance is actually DAB here. Yeah. Yeah, so the way to think about that is when we choose B, we have only one thing to specify. Because it must be distance DAB from A, then you specify it with a single angle that indicates like, where is B on the circle that is centered at A. everyone see how that works? Like, we had two choices. We had two numbers to specify for A, but we have one number to specify for B, based on the constraint of a rigid body. Yeah, but the whole point here is to show what are the number of degrees of freedom of a rigid body. What about C? Like, how many choices do we have for that? I'll let you think about it for a few seconds. Yeah. You can kind of tell from the figure here, right? How many choices do you have for where C can go? Anyone? Yeah. So, yeah, yeah. Yeah, so if you're given A and B, C is fixed basically. So does everyone see how that works? So when you pick A, you have two numbers to specify. When we pick B, we are subject to the constraint that the distance from A to B must be dA. So B must be on this circle. And then when we pick C, so the distance from C to A must be DAC. The distance from C to B must be DBC. Yeah. I thought and when you do that, when you draw it out, then you only get basically one choice. Now, strictly speaking, you can also have this point, like that point there is another one that satisfies the distance constraint, but it corresponds if you flip the coin over. But when we talk about degrees of freedom, we're talking about real values, like continuous values, like not discrete, which is it's a minor technicality, which for the most part, you don't have to worry too much about. Yeah. So you have basically the three numbers due to the three choices that we just made. So that's how you derive the degrees of freedom of a rigid body on a plane. What about if you could just, if it's not planar, like if it's just an arbitrary 3D space, like what would be the degrees of freedom of that? I mean, it's probably going to be at least 3, maybe more. And like, what's a good? Yeah, do you have any thoughts about like the number? All right, so 6. Yeah. So I think whoever said 6, you should also show me how you got 6. We're gonna do that right now anyway. So if you have your rigid body in 3D, then the way to derive the number of the degrees of freedom is that for the point A, we have 3 choices to make. We have an X, Y, and Z coordinate. So that's 3 numbers. It's like unconstrained. For B, we have 2 choices. So it must lie on a sphere centered at A. Maybe I can just draw it out a little bit. It's not too bad to do. So we have A, we have 3 numbers to specify for that. Now we need the distance from A to B to be the DAB. So that's this. So this is like a sphere centered at A with distance with radius, DAB. Yeah. And then to specify B, you pick the latitude and the longitude so that that's 2 numbers. So you might pick B to be over here. And this is at some latitude and some longitude. Now, when we pick C, what we need is the distance from A to C must be DAB, DAC. The distance from B to C must be DBC. So what happens is that we get the intersection of 2 spheres. So So what we get is like the intersection of two spheres is a circle. So it's like the circle that where the two spheres meet. It's a little bit easier to see if you. There might be some videos that show like the nice intersection between two spheres, but this is basically what it's kind of like. You have a circle, then you have to find some point on the circle. So get one choice because you can pick an angle. So get one choice for C. Yeah. And the degree of freedom of a rigid body in 3D would be 6. So, yeah. Any questions so far? Yeah. Because I think I'm understanding rigid bodies, and then later next week when we talk about rigid body transformation, that's a very important part in robotics. So, a very important part of robotics. Yeah. So again, degrees of freedom. Oh yeah, question.
Representation. You have to know how to represent it. X, Y, Z position with visual audio.
Repeat the last part.
I mean, how to represent the degree of freedom, how to write it. So it's like X, Y, Z and visual audio. Or is it
All right, but I think what you're asking is, we talked about the degrees of freedom being 6, but what do those numbers mean? Like, how do you like actually write them out? That choice is I think that choice is different from the degrees of freedom. The degrees of freedom is the minimum number of real value coordinates that you need to represent something, but you can choose a different representation. We'll talk about that later, because you can specify a rigid body with a matrix that had like 10 or 12 numbers in it, for example. And then you would get more things there, even though it's not the minimum number, like different representation have different advantages and disadvantages. So I think what you're describing is a different question that we'll cover. Yeah. Yeah, do you have a question?
Consider 2 points or like the third point is this. So you mind that the circle is this would be the degree of freedom, right?
Well, the circle is just a way for us to specify the number, like how many numbers we need to specify where C should be, like the minimum amount of coordinates that we need to specify where C is. But so again, in practice, when you work with it, you'll pick your own choice of representation. Like you can pick an X, Y, Z coordinate and then like 3 angle, which is the minimum number, or you can pick X, Y, Z and a quaternion, which is 4 numbers, and then that's 7 numbers, because different representations have different advantages compared to this. Yeah.
DBC and DAB stays constant, right? For DBC, DAB and DBC stays constant.
Yeah, well, yeah, they stay. Yeah, here they stay constant. So what we did here was we assumed that we had 3 points, and then these are the constraints that must be true. And then later we used that to derive the degrees of freedom. Yeah. So yeah, this is a way to describe the degrees of freedom. It's like a dimension of the configuration space too. So another way to specify it at a very high level would be the sum of the freedom of the body minus the number of independent constraints. So if you remember the example earlier, with that 2D coin, we had 6 freedoms of the body because there were like 3 points with 2 numbers each, so that's 6 freedom. But we have 3 independent constraints corresponding to all the pairwise distances between them. So it's 6 minus 3 is 3, which is the number of that we derived. All right, so let's talk about robot joints. So what you see here are the most common types of robot joints. Those are typical robot joints that connect different links together. Yeah, so every joint will connect two links. So a joint is something that connects two links, and a link is like some body that the collection of links and the joint form the robot or some kind of system. So a quick question for you. So if you look at this Revolut joint, what is like the degrees of freedom of that joint? Yeah, so it's one. Why do you think that?
Of that one axis.
Yeah, so it can only move about one axis. So another, I think maybe that's a good way to think about it. The way that I might describe it is if movement about the axis can be entirely specified with one number. Yeah. Yeah. Well, so we talked about the Revolut joint, and then there's the prismatic joint. How many degrees of freedom? Yeah, it's also one. What about the spherical joint? It's a little bit tricky to see. I think it's easier if you see an animation of how that joint works, which I think I have it in the video that I'm going to show next. But to summarize, the Revolut, the prismatic, and the helical joint, they have 1 degree of freedom. The cylindrical and the universal one have 2, and the spherical one has 3. Yeah. So, any questions on that? But I'll show an animation of the joint too. So. All right. So Grubler's formula. So this is a general formula to determine the degrees of freedom of a robot or some kind of general mechanism, because when you're dealing with systems that are more complicated, it becomes hard to intuitively think about, like, what's the degrees of freedom. So it's easier if you have some mathematical formula that you can apply. So it looks like this. So the degrees of freedom of a general mechanism is based on the rigid body freedom minus all the joint constraints. So n is the number of links, which also include the ground. And we'll see some examples of this later, but when we talk about ground, like, the ground is often drawn like this. If you look at modern robotics, they draw the ground with this like jagged line. So the ground is like one link. And you can have multiple ground if the system is connected to different parts. Like, you can think of this as a floor and this as a wall. But all of it is considered one ground. So, yeah. All right, then J is the number of joints. So remember that joints connect links, but they're not the same thing. Joints are not the same thing as links. M is the degree of freedom of a rigid body, where we have F is the degree of freedom provided by joint I, and then C is the constraint provided by joint I when we add in the subscript here. So if this all looks a little bit unwieldy, in practice, usually the formula is a lot simpler to use. Like, in practice, M is usually 3 or 6 because we're usually dealing with a planar robot or something in 3D space. And F is the degree of freedom provided by the joint, which we basically covered last slide. Like, there's basically 6 common types of joints. And even of those 6, you usually only see the first 2, like Revolut and prismatic. which have 1 degree of freedom. So usually the last sum is like a sum of I equal 1 to j of 1, which means it's equal to j. Yeah. So in practice, the formula is pretty easy to use. Yeah. And if you want to know what to put in for F, you just look at this table. So revolute means you get 1 degree of freedom. Now, same thing with prismatic and helical. And then for these, you get 2. Then for spherical, you get 3. So, yeah. And this is how they derive F, but to use the formula, you don't actually need to know like this stuff. You just need this column. All right. So I wanted to give a visualization of how the joints move. So this is going to be what a revolute joint looks like. So yeah, this is what it looks like. So you see that it has one place where it can rotate, and then you get one number to specify that. So that's why you get one freedom here. Yeah. Up next is the helical joint or prismatic joint, sorry. Oh yeah. So oops, sorry. Yeah, so this is the prismatic joint which slides across something. This is another universal joint. That's another one that was in our table. So that's why it has, all right, this is the spherical one. Yeah, because you can specify like 3 numbers, like say, 3 angle where it should be oriented. And yeah, this is like a shoulder, similar to a shoulder joint, I think. Yeah, and then yeah, the link to this video is here if you want to look at it in your own time. All right. So let's take a look at some examples of using Grubler's formula. So what we are showing here is an open chain mechanism. And the question we want to ask is, how many degrees of freedom are there here? And the way to interpret this diagram is that this thing is the ground. So I drew the ground. So that's what this thing means. So we have the ground that like fixes the robot. And each of these circles represents a joint. And when we draw them, it's going to be the revolute joint because this is how you usually draw them, like they rotate about something. So what do you think the number of here would be? Like how many degrees of freedom? Oh, you're saying 4? Why? Yeah, so every joint here would have 1 degree of freedom, and then there's 4, then yeah. But let's show that Grubler's formula results into that. Because sometimes when it gets more complicated, it's gonna be hard to think like that. So yeah. So in general, this is a K-link planar chain. So it's operating in the plane. And n is K plus 1. So why are there this many links? Well, we have one link, which is the ground. We have this other link, and then we have ground, this link, this link, this link, and then that link. So there's 4 links plus the ground. So that's 5. And we have the 5 in this case. And then there's K joint. They're all revolute, so there's 1 freedom for each. Yeah. And if you do the math, you get, 3K plus 1 minus 1, and then the entire thing here goes away, then you get K here, which is the number of joints K, then it's this thing. So you get K joints. Right. What about this? the way to interpret this diagram is that this is ground, but the other jagged lines that you see there, they're also ground. So you consider them as like the same link. They serve the function of like stabilizing the robot. And what you see here is a single, there's a revolute joint here, but there's also like a prismatic one that slides across this axis. So how many degrees of freedom here? I'll give you a couple seconds to think about it. Hmm. All right. Well, let's see what it is. So we have n equals 4. We include ground, but that's only one. So we have one ground, we have this link, we have this link, and then there's considered to be another link along the sliding part. And then there's 4 joints. So there's 1, 2, 3 revolutes, but there's also a prismatic one that is like at the same thing here. And the degree of freedom would be 1. All right, everyone see how that works? You don't get 4 here, you get 1. If you want to visualize how it works, then here's the way that I think about it. If you specify where where this thing should be along the prismatic joint, once we pick that number, that fixes the rest of the system. It can't vary. Because if I fix this to be here, then I can't I can't move this that thing gets stuck. So yeah, there's 1 degree of freedom here. All right. Any question? All right. All right, so now we'll talk about a configuration space and a topology. So the reason for this is that we've talked about degrees of freedom, but you can have the same degrees of freedom for 2 configuration spaces that are fundamentally different in some sense. And so that's where the topology comes in. So for example, if we are trying to specify a point on a plane and a point on the sphere, both of them have a 2D configuration space because for a point on the plane, you specify it with the x and y values. For a point on the sphere, you specify it with the latitude and the longitude. So it's 2 numbers for each. But do they have the same shape? You have a plane and then you have a sphere. How do you define maybe you have some intuition here, but it somehow feels that a plane and a sphere are topologically different. So if you want the intuition, the way to think about it is if you can continuously deform one space to another without any sort of cutting or gluing action. And if you want some videos, I think the modern robotics video, they have some examples of how the continuous deformation part would look like. But here's a very quick example. If you have this open interval, it's A, B, but doesn't include the endpoint, then one thing you can think about this is by specifying it as the open like half circle. So you can talk about this open like half circle. And if you have a point here that you shoot out like rays from, then you can get a correspondence between a given angle here and a given point on this real line. And so these two, like the real line and this half sphere, they're said to be in some sense like topologically equivalent because you can continuously deform them, and then for every single point on this half circle, you get one point on this like in an open interval. But yeah, if you're talking about the closed interval, then the closed interval AB, when you include the endpoint, is not topologically equivalent to the open circle, because if you make your point equal to A, then there's no like corresponding, you can't do a continuous deformation that would map point A to point A on this open interval, because it also, by definition, it doesn't include it. So here's some examples of topological spaces. This is the space of a single circle. So we denote this with s to the first power. And this thing will specify, you have one number to specify, and that is like some topology. That is your topology, basically. So yeah, you can use this to specify things like, what is the topological space of like one, revolute joint. Yeah, because you have like one joint that can map to, assuming you can map it to every single angle, which may not be true in practice, but no. Yeah. So another space is, what happens when you combine this with another circle. So this is a torus. When the space is S1 times S1 equals T squared. And if you want, you can flatten the torus into a plane to represent points as like x, y, like or with two numbers like theta1 and theta2. But the plane and the torus are not topologically equivalent because you cannot continuously deform a torus into a plane. Yeah. And do you see why this is the topological space of two, in some sense, two circles, right? Because you can specify one circle in terms of like, you specify one angle for like the, I guess, what do you call it? Like the thin part of the torus. And then you have like, when you take out a top-down view, you can also think of it as another circle to indicate like, where should you be on this bigger circle? Yeah. So yeah, you have two numbers to specify, then you can be like anywhere on the surface here. But again, the reason for showing this is just to show like, how can we specify this with like two numbers? But there's going to be a discontinuity here, like, right? Because if you go from like 2 pi to 2 pi plus some small number, it gets back to 0. Just because like when you have angles, they wrap around with 2 pi. Again, these two things that you're looking at are not topologically equivalent. All right, and then what is the configuration space with respect to topology for a 2-DOF planar robot? I guess what's the topology of its configuration space? I mean, I kind of gave it away here, right? There's only a few candidates, right? multiple choice. I'll give you a second to think about it. And I should have also added, we're making some assumption here like that. When you have like this revolute joint, like it can go like anywhere across the from 0 to 2 pi. So there's no constraint on that. And the same thing for A, like the A is the revolute joint where it can go like anywhere across the 0 to 2 pi interval. And B is just an end effector. So B is like not a joint. The end effector is very important though. We'll talk about that, but it's not a joint.
Equals what? Q1 plus.
So what are you saying? Are you talking about like what is the configuration space of this? What is it? Yeah, what is the configuration space? No, I think you're talking about the workspace, like all the valid configuration where the end effector can be. Well, that's the workspace. So the configuration space is how do you specify like where the robot is? Like they're not the same because you can have an end effector of the robot to be in one spot, but with different joints that lead to the same thing. Here I think you could get it if depending on if A flips to the other side, then you get things like that. So if the robot is like this, but if it's dead here, you get a different configuration, but it gets the same end effector. Yeah. Yeah, so the configuration space topology for this robot is the torus. It's the same thing as this. So if this is confusing, let me show the video here. Yeah, so this is the process of how to convert from a torus to a plane. So I think you cut it and then you flatten it. But because you do that, it's not topologically equivalent because we had to do the cutting. At this point now, I think coming up later, it'll show like for the 2R robot arm, what is the topological space, which is going to be the torus. So this is the system. And if it moved with one, this is the representation. And this is the visual of like the point that specifies where the robot is. So do you see what's going on in this animation? You have a system which is the same as what we're showing here. This is the visualization of the topology, where every single point, like this point on the torus surface, represents one configuration. So every single configuration of this system can be identified by one point here. This thing is just how do we represent that in our how do we choose to represent it in like our code or map, for example? That is like two angles, but it has the problem that you have a big jump when you go from like 2 pi to a little bit more than that. So let me show this again. So this thing is moving, and this dot is showing where it's moving. If it's the other one, then it goes about the other circle that we talked about. Then if both of them move, then it can move like anywhere on the surface. All right, any questions on this? Yeah, then you can look at this video at the bottom later if you want to. All right. So we talk about the topology, which is the fundamental property of this configuration space. So it's independent of how we choose coordinates to represent those points. So to represent points on the unit circle, you could choose to say, well, let's say we specify with an angle theta from the center of the circle relative to a given like zero angle. So if you choose that, you are representing this with one number, the angle. You could also choose a different representation based on use two numbers subject to the constraint of x squared plus y squared equals 1. So you have the same configuration space, but you have different representations for how do we, indicate a given item in the configuration space. Right? So hopefully this is clear because I think this idea is very fundamental. So it'll come up again next week when we talk about representation for rotation, for example. And the one reason why it's so important to understand what the representation is because you could have different representations for the same configuration space, but they have different trade-offs. So if you are working with something for your own robotics application, you will often have to make a representation choice. One distinction between representations is an explicit one versus an implicit one. So an explicit representation means you are using the minimum number of coordinates for a configuration space. So if the configuration space is n-dimensional, so it's n degrees of freedom, because degrees of freedom is the minimum number. An explicit one is n parameters, an implicit one is uses more than n parameters. So if your configuration space is the sphere, like point on a sphere surface, then what is an example of an explicit versus an implicit representation? So the surface of a sphere. I'll let you think about it. I mean, if you're on the surface of a sphere, think about if you're on like the planet Earth, right? Like what's the minimum number of numbers you use? What's the minimum amount of like coordinates that you need? Yeah, so latitude and longitude are like two numbers that you can use. And then if you know them, then you know like where you are on the surface of a sphere. An implicit one is something like this. So if you assume that the radius is 1, then you have three numbers, x, y, z for a position, subject to a constraint that x squared plus y squared plus z squared is 1. What's good and bad about these? Like why is latitude and longitude not good? Latitude and longitude, they can be good, but there's very obvious drawback to them.
Your latitude and longitude are putting the surface, whereas like the implicit representation also happens. This is from the center of the sphere. So it would be like underground.
Well, I think we're just assuming that we're just going to make the assumption that we only care about the surface of a sphere. So I don't think we need to worry about like if it's like not on the surface. So the real weakness of latitude and longitude is like maybe I can draw it out. So latitude is like something like this. So all right. So the latitude is like I don't want to call it height, but if you're like looking at this, you can think of it as like a height thing. Then longitude looks like what? So. So it continues like this. So what happens if the robot is over here? No. If the robot is at the very top here, what's the latitude and longitude? If the robot is taking very small steps, if the robot is taking very small steps around the North Pole, then the longitude is changing a lot. Because if we're over here, like, it takes an agent to go from, one part of, like, if you're looking at the Earth's equator, then you can go along like this direction, but it takes you a very long time to do that. But if you're at the North Pole, then like at the limit, if the North Pole is like right next to you, like a foot away, then you can just walk around it very quickly. And then your longitude changes a lot. And that kind of big change is sometimes not very desirable to robotics algorithm. So and more generally, it also means that, if you're trying to determine like where should you move the robot based on its current coordinate, then you might have to make your model would have to consider where the robot is. Like if it's at this location, you really have to be very careful. But if you have like an XYZ subject to the constraint, then the changes are going to be the same no matter where you are. So the North Pole and the South Pole, they're called a singularity of the representation. Yeah. So the issue with the explicit representation is, what happens at the pole? And the issue with the implicit representation is that you have to specify more numbers. But personally, most people, when they talk about position, they usually use like implicit representation. You can use explicit one. I think using an explicit representation is good if you expect that your robots are not going to be near the singularity. That could be one good reason to use the explicit representation. But again, it depends on whatever robotics application you have. Like if you have to use the knowledge of where you expect your robot to be, and then that can inform you which representation you might want to use. Yeah.
The thing is the visual on your with the same distance to the center of the school. So if this model uses that.
All right, so you're talking about a different representation. You can use pitch and roll to specify where it might be on the surface of the sphere. Well, yeah, maybe you could. Maybe these are just two examples. I'm sure there's other that you can use. Yeah, but again, this is not meant to be an exhaustive set of representations, just like two common choices. Yeah. Oh yeah, so quick topology recap. So here are some common systems with their topology and an example representation. So again, the last column is an example. You could argue that for your own application, you should not use that representation. You should use something else. That's totally fine as long as you justify it. So we have our systems here, like you have a point on the plane, you have a spherical pendulum, you have a 2R robot arm. That means like two revolute joints. It's the same one that we've been talking about earlier. And then a rotating sliding knob where you can have one rotation and then one, prismatic joint. Yeah. And again, to reiterate the point, the representation is just a sample. You might want to use a different one depending on your application. So if you look at the topology here, a point on a plane, you use the topology like the plane. So Here we're denoting that with E squared. And a sample representation of are the 2D, XY coordinate. I mean, most people would probably use that. But of course, there's other thing, maybe polar coordinates. So a spherical pendulum means the topology is this thing, which is the surface of a sphere. And an example representation is the latitude and longitude that we just talked about. Your 2R robot arm, the topology is not the same as a sphere. It's a torus, which is the composition of two single circles. Yeah, so these two are not the same thing. But you could also represent it with two angle-like things. So, you can use again this representation. So, now for a rotating sliding knob, the topology is like a cylinder because you can move all across the longer part, and then the rotation is about like the circle. Like if you take a cross section, you get a circle. And the sample representation would be the real line, the composition of the real line with an angle. Yeah. All right. So I think this is a good time to take like a quick 5-minute break, and I'll just let you look at this. So yeah, have a good break, everyone. Usually people get up and do something. Yeah. Mhm. Hey, you have a question about this? Oh, about what?
Group years, for like the formula I used to calculate degree.
Oh, yeah.
So like in that, M is the number of, I didn't understand the bracket for it. M is number of joints. And
Oh, yeah.
and lanes. Like this,
Yeah, so M is like the degree of freedom of a rigid body. In practice, it's only gonna be 3 or 6 for things. So 3 if it's like a planar thing, and then 6 if it operates in the whole 3D world. So
okay,
the way that it works is because you have M multiplied by the rigid body.
yes,
If I have this many links multiplied by the freedom. So if it's only planar, then
okay, so like if
three
it is in
numbers.
2D, then means consider three into number of joints and the number that we got, N and J.
Yeah, well, yeah, to summarize, for anything that you now is only going to be bigger space, three. Oh, yeah. Yes. Okay. Thank you. Yeah, by the way, when you write IMX now, I would recommend you write more things about yourself. I think I think I think Hydra, it's kind of fun. Yeah, some cool,
I saw, okay,
keep following up with them, because I think if you, yeah, it'll be. I mean, we can try that out, which groups, are available. Yeah, I think just make sure that you are, proactive in that. All right, maybe we should get started. Any last minute questions about the topology recap? Right? All right, let's look at some examples. What would be the way that you write out the configuration space of a mobile robot translating on a plane? And hopefully at least the number of coordinates that you need is clear. I'll give you this. Oh, okay, so you beat me to it. Okay. So you could write it as r squared. So that's one way that you could write it out. What about if you're doing what about if you have a mobile robot that is translating and rotating on a plane? Someone said 3, someone said 6. I think it's 3, but you have to be careful how you describe it. So the way that we often denote it is with the special Euclidean group. So we'll cover that, I think, next week, but SE3, SE2 is the Cartesian product of your R squared, which is like the planar thing, crossed with S1, which is your sphere. So you get one choice for the angle, and then 2 choices for the position. What about spacecraft? Assume that it's rigid. Because if it had like a bunch of deformable parts, then forget about it. So we would write it as the special Euclidean group with 3 there, because it's the Cartesian product of 3 numbers for the position component, and then this is the set of all possible like rotation. Typically, it's like the set of all possible rotation matrices, which specify the complete orientation in 3D space. So the bigger point here is we could have replaced spacecraft with basically anything any rigid object operating in 3D space. That's the point here. The point here is not to be concerned about a spacecraft, but an object in 3D space. That's rigid. Yeah. An end-joint revolute arm. So that means you have, it's like the sequence of open chain arm that we saw, but you have like an arbitrary number of revolute joints. So that would be T to the n power. So it's the Cartesian product of this thing with 1 for every single joint. And then if you have a mobile robot with a 2 joint arm, then you get your special Euclidean group with the parameter 2 along with the two joint arm. That's like you have a two joint arm and then it's attached to a mobile base that can move and rotate. Yep. So these are some examples. All right. So yeah.
This would be, or as
So this is like, R is like the set of real valued numbers. So this is just your set of real valued numbers. Like when you have R to the some power, that means it had that many numbers in it. So R to the third power is something that represents the set of all possible like 3D numbers. So if you remember, we talked about like vectors. So if you have like three components in a column vector, then that vector is a member of R cubed. And T is, so we have T is just the combination of different S1. So if you have T to the end, it's the same as S1 S S1. And so you have n of these things. So you can get one of these to get a t to the n. So we talked about the torus, which is t squared, because you have two circles that are part of it. And then SO and SE, we'll cover those next week. Those are like a special Euclidean or the set of orthogonal matrices or rotation. So yeah. All right, so armed with the knowledge of configuration spaces, we can now talk about a path planning problem. So we have we desire a continuous mapping function such that no configuration in the path causes a collision between the robot and the obstacle. So we have our circular robot. It is centered here to represent the set of points that the robot occupies. You can mathematically denote it as something like this. So R of X and Y is equal to the set of all possible 2D points such that, the point XY is within distance, or if you square, I guess if you have the distance is less than or equal to R. Yeah, here we're just squaring everything, but it's the same as like the distance has to be less than or equal to R. So again, this represents a set of all possible points that the robot occupies. So it includes the interior. Yeah. Because when we're doing path planning we're trying to find a collision-free path such that the circular robot can go from your the initial pose to the target. And we have to consider every possible point on the robot. You can't just consider the center because can the center be like right next to an optical if the radius of the robot is actually much bigger than that? Yeah. So yeah, if you ever had like a Roomba robot like knock into a door, then you run into that problem. Yeah. I think actually I think this thing is 0 to 1, but it should probably be replaced with like your more generally like I think this is just some general space of maybe the workspace, and then we map it to the set of configurations that are valid for the robot to take for a path. Yeah. We're going to see an example of this pretty soon. All right, so if you have optical I, and you have Q be the XY coordinate of the robot, then the set of configuration where the robot intersects optical WOI. All right, so what this means is this thing here is the set of all possible configuration. In this case, is all possible 2D coordinates, such that the set of all points that the robot occupies intersection with the optical is not equal to the empty set. Let me- All right, we have some obstacle here. Now, if we want to find something that is inside this set here, then maybe we'll pick this. All right. This is an XY. This is some configuration that specifies where the robot is. Now, RQ, that's this is all the possible points that the robot occupies. Now we wanted it to intersect, we intersected it with the point in this obstacle. So it's non-empty, right? It's not equal to the empty set because we have this region here. We have this region here, so this value of Q is inside that set. So, yeah. How do we write out the set of configuration where the robot does not intersect any obstacles? So the thing that you have to do here is you consider all the obstacles. So whatever we write here is probably going to be like the union of many different obstacles. Yeah, but you can have different obstacles. You can have this one, and then you can have this one. Another obstacle here is you can have this one here. Yeah. And yeah, this one is also intersecting here. So in this case, it intersects with two obstacles. But in practice, if it intersects with just any obstacle, we just call that as being as not being in this space. I mean, the reason is, in practice, we usually want robots that don't collide with things. Yeah. So we get Q3, which is the set of all possible 2D points, such that it's not in this set, so it's not in the union of all the set of configuration where the robot intersects any obstacle. Yeah. So Q3 is like maybe if the robot is over here, this Q is gonna be in Q3 because it doesn't collide with anything. So. And then this will help us define a free path. Well, I guess this is probably denoting like time. So you get like time from 0 to 1, if you normalize it to the scale, and then you map it to something in Q3. So if you look at this example circular mobile robot, imagine we have that single robot and one polygonal obstacle. So that's what we have here. So we have our single robot, and then the obstacle is over here. Now, what do you think is happening here? Yeah, so the circular robot is like walking across the edge of the entire polygon. What do we get from that? Like, what do we get from that? Like, you have this, and then you've got this curved shape. What is this thing representing? Well, yeah, the free area, if you're talking about the point not in here, and by free area, we really mean the free configuration. Because what's happening here is we're trying to find all the points that can go like as far as they can to the optical without like actually going through. And because we specify the configuration with the center of the circle, then what we're really getting at is no. Anything outside of this curvy shape is in like Q3. Yeah. So that's why whenever we have an optical, it's not the case that you could just go to automatically say everything not in the optical is the free space, right? Because you can't have the circular robot, even intersect it. So that's why you always need to have some kind of gap between the center of the robot and the optical. So how do you define the valid configuration of the robot? In this example, you trace the robot around the optical and you connect the center point. And then we have all the configuration where the robot intersects this optical. And one advantage of doing it this way is that if you have many different circular robots, you can use this analysis to reduce everything to single point mass robot. Like the robot is a single point. Then with different with optical that represent where that point cannot be at. Yeah. So all right, question? So I was talking about what happens if we have circular robots with a different radius. So here we have a single point mass. Here we have a bigger circular robot, then here it's even bigger. Imagine your Roomba, right? You have a big Roomba, you have a small one, and then you have one that's like so small it's not even Roomba. So what are we looking at here? Like what happens when you have a bigger robot? If this bigger rectangle represents the boundary of like your room, for example, what's going on here? Like, can we go from here to here? Like these points are like a start to the final. So in all three of these, we have the same room, we have the same optical, but we just have different robots. And we have the same starting and the ending configuration for all three of these. So what this is really showing is that the bigger the robot is, the more likely it can't find a collision-free path from one to another, which makes sense, right? Like if the robot gets too big at some point, it's just gonna bump into optical. So yeah, this is one way to visualize and like sort of reduce the analysis of these three different robots to a single point. And then you could just run like some kind of search algorithm to see if you can connect the 2 points. We're going to talk more about that in about 2 weeks after the spring break about like motion planning algorithm. So yeah, but for now, just think of it as, can you trace the path from, the start to the end? In the third example, you can't, because the robot isn't big enough to go through the gap. Yeah. Yeah. Right. All right, so some other definition to be aware of, and some of you brought this up earlier. We have the task space. So that is a space in which the robot's task can be naturally expressed, right? So it's a very vague, it's a broad term, but just it's subject to your own interpretation. So you can argue, there are different task spaces for the same thing, and you might be right. So if you have a robot that is trying to do something like write on a piece of paper, those robots do exist, by the way. You've seen the robots that have like a pen and then they control it, right? Or paint. Look on YouTube if you haven't seen it, or a Billy or whatever. So if the robot is supposed to write on a piece of paper, then your task space is like R2 because you specify in like X, Y. The workspace is a specification of the configuration of the end effector, that the end effector of the robot can reach. And then this is, so it's driven by the robot structure independently of the task, where the task space is driven by the task independent of the robot. So it's like a different definition here. Yeah. And the main difference between the workspace and a configuration of that, the difference between the task space and the workspace is that some points in the task space might not be reachable, but all the points in the workspace are reachable by some configuration. Because the workspace is defined by what the robot can reach. But if you're trying to do something like that pen writing robot, there are some location in the plane that it can't reach. Like if the arm is like maximally extended in one direction, then it can't go further than that. So, but that point would be in the task space, but not in the workspace. So, yeah, and then I kind of gave it away, but the workspace is not the same as the configuration space. So we'll talk about that next. So, workspace and configuration space. All right, so consider our planar 2R and 3R open chain. So we have, this thing here is 2R, but that means it has two revolute joints. The one by the center and then the one in the middle here. This one here is the 3R open chain. So it has the center, the first one, and the second one. And then the tip is the end effector. So the end effector is just the position of the tip. So think about it for a bit. What's the workspace and what's the configuration space here? Well, what's the workspace here? What do you think? Well, we already talked about what the configuration space was like for the 2R robot, right? We already talked about that. So the configuration space of these robots are not the same. So here's why. Like one of them is 2-dimension, the other is 3-dimension. Because to specify where this robot is, you have to specify two numbers: the angle for the first joint, the angle for the second joint. For this one, you have to specify 3 numbers: the angle for the first joint, the angle for the second one, the angle for the third one. So the configuration space cannot be the same. It's not even the same dimension. In fact, you can still have workspaces of the same dimension, which are still different, but here they're not even the same dimension. Now the workspace, so the workspace could actually be the same. So the workspace could be the same planar disk. Yeah, you see why? Because the workspace is where all is the set of points where the end effector can reach. So if you really want to be precise, you can think of it as an annulus, which means you have a circle, but you have a disk that is where the center of the robot is, like the origin. So it's because the end effector can't like actually be there if the robot base is there. So this annulus is like the workspace for both of the robots. So the reason is, if you have your robot here, you can have it looking like that, and then you can have it pointing here, and so this point is in the workspace. If you want to try another point, then you try this one, then you can have that. So you can pick points here, then there's going to be some configuration that will lead to that. Now you have to assume, of course, that you can actually, rotate the joint like around the full axis, the full like 0 to 2 pi range and so on. But so technically you have to make some assumptions, but I hope that the basic idea is clear. Yeah.
The meaning of the 2D and 3D here in configuration spaces that we use 302 parameters to specify the actual state of the effector range.
Yeah, that's correct. So the reason why we have 2D and 3D is because those are the minimum number of coordinates we need to specify where the robot is. So for a configuration space, we need two numbers because it matters, like this configuration is different from, like you can have this configuration and this configuration. There are different configurations that lead to the same end effector position. But when we're talking about configuration spaces, we need to know the full state of the robot. Because if there's an optical here, but not one here, then we have to avoid this one. So the configuration matters because it tells us, where is the full robot. Yeah. All right. So now let's talk about this example. Here we have our same planar 2R open chain. So the same one from the last slide. But what we have here now is a spherical 2R open chain. So the way to think about this is you still have two joints, but they can extend, it's not planar anymore. So what this formed is a sphere, actually, like where the end effector can reach. So you have like a ground, and then you have this joint which rotates, and then you have another joint which is like in a way that I guess causes a three-dimensional workspace to appear. What about the workspace and the configuration space? Well, the workspace is not the same, right? So like the end effector of this thing is 3 dimensions. It's like a 3D sphere, which is different from a disk. But for configuration spaces, both of them you can express them as 2D, right? Because you can express an angle for the first joint and an angle for the second joint. So it's this T squared is the configuration space topology. So they actually have the same topology for configuration space purposes, except they don't have the same workspace because you have a planar disk versus the surface of a sphere. So we talked about this example where the configuration spaces match, but the workspaces don't. But in the last slide, it was that the workspaces matched, but the configuration spaces did not. Yeah. Got it. So another way to think about like, configuration spaces and, obstacle there to consider this example where you have a two joint planar arm. So it's the same one it's the same one to the left here that we've been talking about. Like a two joint planar arm where this thing at the bottom is like your starting pose. This thing at the starting end effector configuration. And this is the last thing, your desired like end effector. Then, this thing is the starting robot pose. This thing is the ending one. Yeah. So we have a 2R robot. The configuration topology is a torus. Now, what's happening here in this figure is that we're trying to map point on the torus to point on the grid. So you saw the example video from the modern robotics video where they show the animation of cutting the torus and then mapping it to a plane. That's basically what's going on here. That's how you get to this diagram to the right. Yeah, so you define a grid on the surface of the torus, where each point on the surface of the torus is like some configuration of the robot. You map it to the grid. You can do the same thing for the obstacle, right? And what you get here, if you visualize this, like this is a visual, like if you had like a top-down view, then you just saw the robot. But right is the C-space visualization, like the configuration space of both the robot and the optical. And they're color-coded, so you see that like this is the darkest optical, and then it maps to here. And then, yeah, when you're mapping from a torus to a grid, you get these patterns like where there's like vertical lines, but that's because there's discontinuity. And if you see the videos of how you map from the torus to the grid, that's how you get to this pattern. And these set of dots are the points of the robot as it moves through this path. So again, this to the left is like a visualization, like a top-down view. If we have a camera and then we're just looking at it. This is if we mapped everything over to configuration space in a grid, and then we saw, these are all the opticals. Here's where the robot is. And here it looks like it found a collision-free path from one to another. Yeah. So yeah, the advantage of doing this is that if you do this, you can quickly get a sanity check. So if this thing were to intersect an optical, you could immediately say, well, no, we have to find something different. So like this type of mapping can be a useful technique for double checking, the motion planning of a system. Right. So again, if this is confusing, you should just look at the video that I shared, and also this is also in this other textbook. So we have two textbooks that they give basically similar things, but one book is more recent, so I usually use the modern robotics one. But the one here, Principles of Robot Motion, is also very good. All right, now what happens here? So imagine to the left, that is our starting pose. To the right is like our target pose. So the robot has to go from, the start to the end. Can it do that? You can kind of think visually about how the robot would move, right? Yeah. So what happens if you try to go from the start to the end? Like there's going to be an optical, right? Yeah, but if you think about this, like what happens if you try to deform it? Like you try to change the angle of the first joint and the angle of the second joint, no matter how you try to change it, you cannot get the robot to go to here. Because this, especially this optical and this one are gonna block it. Yeah. So that's why you get something that blocks it in the grid representation when you map everything over to a grid. Right. All right. To summarize, we covered what does it mean? What does degree of freedom mean? What does configuration spaces mean? What does the topology mean? We talked about some examples. Then coming up next week on Monday, we have a bunch of mixed topics. So we have some guest lectures on Aikido, which is a software that you'll need for lab 3. So hopefully you'll check it out. We will also have some advanced topics as well as a midterm review. So I'll try to come up with some example problems and then we can go through them together. So hopefully you can be there in person. The following class, we will talk about kinematic transformation. Then after that is the midterm. So, yep, that's all I have for today. And I'll see you on Monday then.